Hi, this is John Whitaker for the Probability 1 class, and this is our 16th video lecture. And last time we ended with the weak law of large numbers, which we said was an example of a convergence in probability. And that type of convergence prompted us to look at different types of convergence. And we ended the lecture with looking at pointwise convergence. And that's something that was studied in Analysis 1, along with something called uniform convergence. We won't look at uniform convergence in this class, but rather what we'll turn to after pointwise convergence is something called almost sure convergence. So let me write up its definition. A sequence of functions. And here when we think of functions, we're thinking of random variables in the probability class. F sub n defined on a common domain we call that domain A, converges almost surely that's what I'm defining, almost surely, to a function f, okay, with respect to a probability if the probability of the set of all x's in A, okay, such that the limit as n goes to infinity of the absolute value of f sub n of x, go left, minus big F of x is bigger than epsilon equals to 0 for every epsilon greater than 0. So this was greater than or equal to epsilon. I'm not sure that's in the frame. I think it is. Okay, what that says that is the probability of the set of input values where f sub n of x does not converge to f of x, big F of x, is 0. So, without listing a specific definition for the probability I'm going to use on 0, 1, let's go back to the example we had before. That is where we have a sequence of functions f sub n of x defined to be equal to x over n, or x to the n, I should say, sorry, on 0, 1, okay? Then, here's what I'll say. This converges to big F, I'll call it F star, of x equaling to 0, okay, almost surely. So A dot S stands for almost surely.
And remember, we had shown that, or used as an example, that the x sub n's, x to the n on 0 to 1 converge to 0 if x was in between 0 and 1, not equal to 1, but equal to 0, and 1 if x was equal to 1, point-wise, okay? But here, what we're thinking is this converges almost surely where our probability is the length, this is the idea about probability, of the smallest interval probability that contains the event. The set. Okay. So here, the spot where f sub n of x equal to x sub n does not converge to 0 was only when x was equal to 1. But 1 would have probability 0 under this type of idea of probability, because the length of the singleton, length of the singleton 1, the set containing 1, its length would just be 0. Okay? So let me write a little bit conclusion of that. So this is where the probability where it doesn't converge, which was the only that number 1 inside the interval 0 to 1. Okay? Probability of this is equal to 0. Now, as a fact, pointwise convergence implies convergence almost surely with respect to a probability. Another type of convergence is convergence in probability, and that's what we have with weak law of large numbers, I should say, weak law of large numbers. So definition, a sequence of functions f sub n of x converges to a function L, df, in probability if the limit as n goes to infinity of the probability of the set of x's in A such that the absolute value of f sub n of x minus f of x is bigger than or equal to epsilon, if that is equal to 0 for every epsilon greater than 0. Okay, in terms of their definition, the difference between convergence in probability and convergence almost surely is where the limit happens. So in almost surely, we're having a probability of a limit. Here in convergence in probability, we're having a limit of the probability functions. As a fact, what we have is almost sure convergence with respect to a probability. Implies convergence in probability. Okay, so that's something we won't prove, but point-wise implies almost sure, and almost sure implies convergence in probability. I'd like to show you a very interesting example to show that just because you converge in probability doesn't mean that you converge almost surely. So the converse of this fact is not true. And so here, let's start off with consider, so as an example, well, let me write this down. To show an example of a sequence of functions which converge in probability but not almost surely with respect to the probability. Okay. We will consider the following sequence. And I'll draw them just to give you the idea. I won't define them so rigorously algebraic. It can be done, but I won't do that. But I think the pictures will give you the ideas. I hope I can use the pictures to explain it well enough. Okay, so we'll consider the sequence of functions whose first few functions are given graphically as so we're going to find f sub 1. And what it looks like, we're just going to define it on 0 to 1. Every function that we work with is going to be on 0 to 1. And this guy's going to be defined to be constantly 0. So that's f sub 1. F sub 2 of x is going to be defined to be equal to 1 on 0 to 1. So it's always 1. So we're kind of going to have a group of these sequence of functions, and we will consider. So here's our first group, f sub 1, f sub 2. Now, here's what I'm going to look at f of 3b. It's going to be defined on 0 to 1. And if you will, we're going to start off up to 1/2. It's going to be defined to be 1. And then this is 1/2. And then after 1/2, it's going to be 0. Then f sub 4, it's going to be defined from 0 to 1/2, and then from 1/2 to 1, to be kind of the opposite of f sub 3. So it's going to be 0 up to 1/2, and then it's going to be 1 from 1/2 on. Okay? So what I want you to notice here in the first grouping, f sub 1 was always 0, f sub 2 was always 1 over the whole interval. Here, f sub 3 and f sub 4, half the time, the interval from 0 to 1, it's 1, but it's a different half the time. Okay? So here's the first half, f sub 3 is 1, 0 otherwise. Here, the second half, f sub 4 is 1, but it was 0 in the first half. And our next grouping of these sequence of functions, I'm going to look at f sub 4, 5, 6, and 7, and 8. So I'll look at 4 of them. Okay, so here, f sub 5, what we're going to define it to be, so it's over 0 to 1 again. Okay, we're going to split 0 to 1, this interval, into 4. So we have 1 4, 1 half, 3 fourths, 1. And from 0 to 1 4, we're going to find it to be equal to 1. And then the rest of the way it's going to be 0. Now for f sub 6, here's 1 4, here's 1 half, here's 3 fourths, here is 1. For f sub 6, it's going to be 0 on the first quarter. It's going to be 1 on the second quarter. And it's going to be 0 the rest of the way. F sub 7, so here's 1 4, 1 half, 3 fourths, 1. It's going to be 0 up to a half. And then from 1 half to 3 fourths, it's going to be 1. And then 3 fourths to 1 is going to be 0. And then f sub 8, there's 1 4, 1 half, 3 fourths, 1. It's going to be 0 up to 3 fourths. And then the last quarter, it's going to be 1. That's what we're going to find. And here's what I can tell you. In each of these groupings, the first two groupings, next two groupings, the next grouping of 4, what we're seeing is that the spots where the functions are non-zero, that interval where it's non-zero is reducing. So here, for each one of these functions, the spot where it's non-zero, the measure for it, is 1 4. Now for my next grouping of functions, I'm not going to write them down, I'm just trying to give you an idea. I have 8 functions, f sub 9 through f sub 16. And they would be equal to 0 most of the way. The only time that they wouldn't be equal to 0 is on an interval of length 1/16. And so what you can see through these functions, if you look at the measure, the probability, I should say, of the sets as we go further and further along in these functions, where where the function is not equal to 0, then that limit is going towards 0. You see, in this two groupings, 3 and 4, functions 3 and 4, the spots where the functions were non-zero was a half. Here, the spot where they're non-zero is a probability of 4, if we think of it as just being the length of the interval where it's not 0. And in my next grouping of 8 functions I'm going to have, it will be non-zero over a length of 16. But if you look and you keep on this pattern, none of the points do the functions for no specific x value between 0 and 1, do the functions converge to 0 themselves for each individual. Okay? Because they're always bouncing up up between 0 being f of whatever that function being equal to 0 or 1. Okay? So it doesn't converge point-wise, but here's what I can say. These this sequence converges in probability to f of x equal to 0, but does not converge almost surely. Not converge. Almost surely to 0. Okay, so it's an interesting example. Well, there's one more type of convergence, and we'll get to it today. But at this point, we're ready to talk about the strong law of large numbers, it's a limit theorem, and do its proof with a modification to the statement, or at least we'll assume something in addition to the statement to prove the strong law of large numbers. Okay, so here's the statement. It says, let x of 1, x of 2, so on, be a sequence of independent variables that are identically distributed each having mean, that's its expected value, equal to mu, and variance equal to sigma squared. Now, we don't need to have anything about the variance, I'm sorry. Each having mean mu, okay? Then, I'm sorry, with probability 1, that means almost sure convergence. Almost sure. The x of 1 plus x of 2 plus x of n over n, this limit, okay, equals to mu. That convergence is almost sure. Now, as I said, we'll give a proof here, but this statement is true, okay? But the proof of it is extremely difficult unless we assume a certain other condition. Okay? The statement's true as is, but if we assume one more condition, then that statement with the condition we're going to assume is much easier to prove, and that's what we're going to look at. The proof for the strong law of large numbers is often given in advanced graduate level text. And so the actual proof of this we will not look at. As again, we're going to assume one more condition. So let me write down what the condition is. We will provide a proof with the additional assumption that the expected value of x of I raised to the fourth is finite. Sometimes expected values of random variables are not finite. Okay? So we're going to assume this one is. Okay? So here's the proof. Okay, we let x of 1, x of 2, and so forth be a sequence of identically distributed independent random variables with the expected value of xi equal to mu. So they all have the same expected values, finite. Okay? So the first thing we're going to do is break it up into two cases, the simplest of which is where we have suppose mu is equal to 0. What we're going to consider we're going to consider the sum, or the sequence S of n, which equals to the sum as I runs from 1 to n of xi in these random variables. And we're also consider or examine a certain quantity, an expected value of a certain quantity. Okay, so, and examine the expected value of S of n raised to the 4th. Okay, what is this? This is going to be equal to the expected value of, I'm going to write it down here, of, it would be x of 1 plus x of 2 plus all the way up to x of n times x of 1 plus x of 2 plus all the way up to x of n times x of 1 plus x of 2 all the way up to x of n, and then one more, x of 1 through x of n. So we're multiplying all these together and then taking the expected value. When we do this multiplication, we're going to have a bunch of terms involved in this expected value. Well, I'll say this. Involved will be the expected value of terms of the form. Okay, so first of all, there's going to be x sub I raised to the 4th, whatever that is. So, look, here's what I'm thinking. You're going to have all of these guys multiplied out. Okay? You're going to take the expected value of the terms that you have as a result of multiplying this out. There's going to be an expected value of a sum of a tremendous amount of terms. The terms are going to look like this. But the expected value of a sum is equal to the sum of the expected values. So we're going to be taking expected value of terms that look like this. X sub I raised to the 4th. What else? You could have x sub I raised to the 3rd times x sub j, where I and j are different. You could have x sub squared, x sub I squared times x sub j times x sub k, where I, j, and k are different. Then you could have x sub I squared, x sub j squared. Okay? And then you could have x sub I, x sub j, x sub k times x sub l. So those things multiplied together. So we're talking about 1, 2, 3, 4, 5 terms that we'll be taking the expected value of. Let's look at some of the expected values of some of those terms. Okay. The expected value of x sub I to the third times x sub j. Now, these guys are independent random variables, and I should say, okay, so they're independent random variables. So that's what's going to give us here is this is the expected value of x sub I to the third times the expected value of x sub j. I is different from j. But the expected value of x sub j, that's the mu, but we're assuming mu to be equal to 0 in this case. So we get 0. The expected value of x sub I squared times x sub j times x sub k, well again, due to independence, this is going to be x sub I squared's expected value times the expected value of x sub j times the expected value of x sub k. Okay. And here, the expected value of x sub j and the expected value of x sub k are both 0, so we just end up with 0 here. This term isn't important, if you will. And in the third type that won't be important, you have x sub I times x sub j times x sub k times x sub l. Due to independence, that's going to be equal to the expected value of x sub I times the expected value of x sub j times the expected value of x sub k times the expected value of x sub l, each one of which is 0, so you just get 0 here. So, the expected value of this f sub n raised to the fourth is really going to be equal to a summation of terms. So, some of the terms are going to be expected value of x sub I raised to the fourth. And here, that's going to be I running from 1 to n. There will be n of those. Plus, well, I'm not going to say how many of them are here, but it's going to be the expected value of x sub I squared times x sub j squared. I's and j's are different. I'm not saying how many of them there are. Okay, it's just some kind of sum that's going to be there. Okay, so that's what we are. Okay. Well, here I know how many of these there are. That's going to be n of them times the expected value of x sub I to the fourth. Well, I should back up. So, no matter what I is, because we have identically distributed random variables, the expected value of x sub 1 to the fourth is the same thing as the expected value of x sub 2 to the fourth, or any other expected value of x sub whatever to the fourth. So if you will, they're all the expected value of x sub 1 to the fourth. So these are all the same for each I. And I runs from 1 to n, so there's n of them. So there's n times, if you will, the expected value of x sub 1. Okay, here, due to independence, we could say this is plus the sum, how many ever there are, of the expected value of x sub I squared times the expected value of x sub j squared. Okay? And similarly, these two guys are going to be the same. No matter what I and j are. And I'm going to worry now about how many of them there are. So, this is equal to n times the expected value of x sub 1 to the fourth, plus, I'm still going to write down the sum, and I'm going to say it's the expected value of x sub 1 squared, that to b squared, because they had x sub I, x sub j, each b squared. So I'm going to say same thing as the expected value of x sub 1, both of them b squared, to b squared. And now I need to know how many of these are there. Well, kind of going back, remember we had terms that, where do they come from? They come from this. So here's what we're looking at, just as a side. We had x1 all the way up to x sub n times x sub 1 all the way up to x sub n. X sub 1, x sub n. X sub 1, x sub n. That was s sub n raised to the fourth. We were taking the expected value of this. So let's talk about what we're going to have squared is coming from. We could have x sub 1 times x sub 1, that's x sub 1 squared, times x sub 2 times x sub 2. Okay? So
let's see, how many of those types are we going to have? Well, for x sub 1s and x sub 2s to be involved. Well, let's see, you have 4 of these groupings. You need to pick 2 of them to be x sub 1s and the other 2 to be x sub 2s. So that's just 4 choose 2 times 2 choose 2. So that ends up being, is equal to n times the expected value of x sub 1 to the 4 plus what's 4 choose 2 for when you have x sub 1 and x sub 2 involved. But you don't have to just have x sub 1 and x sub 2. You could have any 2 variables that you want. And so how many variables are there up here to choose from? Well, there's n. And we're going to choose 2 of them to get involved in this. And then it would be times the expected value of x sub 1 squared to b squared. That's what we have. Good. Okay. This is equal to, so this is n times the expected value of x sub 1 to the 4th plus 6. And then here, this is going to be n factorial over n minus 2 factorial times 2 factorial expected value of x to the first squared, which is equal to n times the expected value of x sub 1 to the 4th. Here, this becomes 3, and then n times n minus 1 times the expected value of x sub 1 squared. All of that to b squared, okay? That's what we have. What I want to tell you is that, what I've just written down here, look, I'll replace this with something bigger, namely n. And so what we get is, I'm going to put in something bigger right now. This is going to be less than or equal to n times the expected value of x sub 1 to the 4 plus 3n squared times the expected value of x sub 1 squared, all that to b squared. Okay. This part's bigger because I replaced, was n times n minus 1 previously. And I replaced the n minus 1 with n, so that's a bigger number. So this quantity is now bigger. Well, we'll stop there for a second and note that the variance of x sub 1 squared, which equals, well, that's got to be greater than or equal to 0. That's equal to the expected value of x sub 1 squared, so that's x sub 1 to the 4th, minus the expected value of x sub 1 squared to b squared. So that means since this is a non-negative number, this guy had to be bigger than this guy. So in our inequality, in our statement here, I say, well, that's going to be less than or equal to n times the expected value of x sub 1 to the 4th plus 3 times n squared, and I'm going to replace this with something bigger, namely the expected value of x sub 1 to the 4th. Now, we're assuming that this is a number. Okay. And so, here's what we have. The expected value of s of n to the 4th over n to the 4th, I'm sorry, the expected value of s of n raised to the 4th is going to be less than or equal to n times the expected value of x sub 1 to the 4th plus 3n squared times the expected value of x sub 1 to the 4th. Okay, now these are numbers. So what I'm going to do is I'm going to divide everything by n to the 4th. And when I divide this side by n to the 4th, I can pull that n to the 4th inside the expected value. So this is a constant. Less than or equal to, when I divide this by n to the 4th, we'll get the expected value of x sub 1 to the 4th over n to the 3rd plus 3 times the expected value of x sub 1 to the 4th over n squared. So we're looking. If I were to sum up all of these, n runs from 1 to infinity, and that would be this sum. But when we sum this part up, I could bring the sum inside here eventually,
And this sum right here, some of these guys, this is a constant, this is a constant, and it turns out each one of those will converge, each one of these series will converge because they are what we call p-series, and p is bigger than 1. So here's what we have. So this says that the sum of expected as n runs from 1 to infinity of s of n to the 4 will be less than or equal to this sum, this expected value of x of 1 to the 4 over n to the 3rd plus 3 times the expected value of x of 1 to the 4 over n squared. Each one of these is a convergent series, and this becomes the expected value of the sum as n runs from 1 to infinity. Oops, this should have been over n to the 4th. S of n to the 4th over n to the 4th. So this expected value is less than this quantity, so it's finite. Or is convergent. That's what I should say. Okay?
So that's what we have. This is convergent. And this can be thought of as the reason that this is going to be convergent. Because it's the same thing as this, and this is convergent because of the comparison test. Okay? This is convergent. Okay, so what that says then, okay, is that, so this summation as n runs from 1 to infinity of s of n to the 4th over n to the 4th, that summation must be finite with probability 1. For if not, if there was some non-zero set where this sum equal to infinity, was it infinity, then the expected value of it could not be finite. It would equal to infinity. And it doesn't, okay? Okay. So that means, with probability 1, so almost sure, okay, if that sum is finite, that means by the divergence test, the limit as n goes to infinity of s of n to the 4th over n to the 4th has to be equal to 0. Okay. But if this sequence goes to 0, then thus, with probability 1, what we have is that will force the limit as n goes to infinity of s of n over n to be equal to 0.
Thus, remember what S of n was? It was the limit, well, S of n was the limit, we have a limit. But the S of n was the x of 1 plus x of 2 plus x of n over n equals to 0. And remember, that's our mu in this case. We're working in a case 1. So that our statement is true when mu is equal to 0. That's what we want to show. And this is with probability 1. Okay, we have to consider the other case, but it goes very quickly. So case 2, is suppose m is not 0, then consider consider the random variables x of I star equal to x of I minus mu. Okay? Then it turns out that these x of I stars, or x of 1 star, x of 2 star, and whatever, and forever, will be a sequence of independent and identically distributed random variables with, if you look at the expected value of x of I star, well, that's going to be equal to the expected value of x of I minus mu, which is equal to the expected value of x of I minus mu, which equals to, well, expected value of x of I is mu, so that's 0. So these x sub I stars are of a sequence, or form a sequence of random variables that fit case 1 type. So by case 1, we have that the limit as n goes to infinity of the x star sub 1 plus x sub 2 star plus all the way up to x sub n star, okay, over n, that equals to 0 with probability 1. So with probability 1, what we have is the limit as n goes to infinity. X sub 1 star is nothing more than x sub 1 minus mu plus, then it would be x sub 2 minus mu plus x of n minus mu over n. That's equal to 0. So with probability 1, this says the limit as n goes to infinity. This will be x of 1 plus x of 2 plus x of n, and then over n. And then you have minus a bunch of mu's. You got n of them. So it'll be n mu over n. So that just be mu will be 0. So that says, with probability 1, the limit as n goes to infinity of x of 1 plus x of 2 plus x of n over n will be equal to mu. And that's the proof of the strong law of large numbers. Ladies and gentlemen, that's enough for today. The next thing we'll do is talk about one more type of distribution just in terms of its name, and then we'll look at the central limit theorem, which is probably, along with the strong law of large numbers, the two most famous theorems in probability theory. Thank you very much.